The brain-machine mirror. How AI and neuroscience are rewriting the rules of intelligence. The human brain processes 80 hours of sensory information every few days. Visual scenes, sounds, conversations, emotions, weaving them into a seamless understanding of reality. Meanwhile, the most advanced artificial intelligence systems struggle to remember what they learned yesterday while acquiring new knowledge today. This fundamental disconnect between biological and artificial intelligence has puzzled researchers for decades, but a revolutionary challenge is about to change everything we thought we knew about both minds and machine. The Argonauts Project 2025 represents the largest attempt ever undertaken to decode how the human brain makes sense of complex, multimodal experiences. Using an unprecedented dataset of nearly 80 hours of brain recordings from people watching movies, this challenge asks a deceptively simple question. Can we build AI systems that truly understand the world the way humans do? The answer may reshape both neuroscience and artificial intelligence forever. For years, the relationship between AI and brain science has been a dance of mutual inspiration. Neural networks borrowed their basic architecture from biological neurons, while neuroscientists increasingly rely on AI models to understand how the brain processes information. Yet this symbiosis has revealed a troubling paradox. The more powerful AI systems become, the less they resemble the flexible, adaptive intelligence that evolution crafted over millions of years. Consider the fundamental challenge facing modern AI: catastrophic forgetting. When a neural network learns to recognize cats, then trains on dogs, it doesn't simply add canine knowledge to its feline expertise. Instead, the new learning actively destroys the old, like a library that must burn its existing books to make room for new ones. This isn't merely inefficient, it's the opposite of how biological intelligence works. A child who learns to identify dogs doesn't suddenly forget what cats look like. Human learning is cumulative, building knowledge upon knowledge in an ever-expanding architecture of understanding. The brain achieves this through principles that AI has largely ignored. Biological neural networks aren't monolithic structures optimized for single tasks. Instead, they're modular, hierarchical systems where specialized regions can learn and adapt independently, while remaining connected to the larger whole. When you hear your favorite song, the visual cortex doesn't need to rewrite itself. When you learn a new language, your mathematical abilities remain intact. The brain has mastered the art of local learning within global coherence. This modular architecture emerges from something even more fundamental: the way biological systems develop. Unlike artificial neural networks that spring into existence fully formed, biological brains grow through developmental processes guided by genetic regulatory networks. These networks act like master conductors, orchestrating when and where different neural capabilities emerge, how they connect to existing structures, and how they adapt to new challenges without disrupting established functions. The Argonauts Project 2025 challenge represents the first serious attempt to bridge this gap between biological and artificial intelligence using real-world complexity. Previous challenges used simplified stimuli, static images, short video clips, isolated sounds. But human perception doesn't work in isolation. When we watch a movie, we simultaneously process visual scenes, dialogue, music, sound effects, and emotional content, integrating all these streams into a unified understanding of the story unfolding before us. The challenge dataset captures this complexity with extraordinary detail. 4 participants watched every episode of the television series Friends, 6 complete seasons, while undergoing functional magnetic resonance imaging. The resulting data represents the most comprehensive recording of human brain activity during naturalistic, multimodal experience ever collected. Every visual frame, every spoken word, every musical note is precisely synchronized with the corresponding brain activity across 1,000 functionally defined brain regions. But the true innovation lies not just in the data scale, but in its structure. The challenge explicitly tests whether AI models can generalize beyond their training distribution. Models trained on friends must predict brain responses to completely different movies, different genres, different narrative structures. This out-of-distribution testing mirrors the fundamental challenge of intelligence itself. The ability to apply learned knowledge to novel situations. Current AI systems fail this test spectacularly. A model trained to recognize objects in photographs often fails completely when presented with paintings or sketches of the same objects. A language model trained on formal text struggles with casual conversation. The brittleness of artificial intelligence stands in stark contrast to the robust adaptability of biological cognition. The brain solution involves three key principles that AI has yet to fully embrace. First, encapsulation, the ability to package learned capabilities into reusable modules that can be combined and recombined for new tasks. Second, hierarchical regulation, higher-level control systems that coordinate when and how different modules activate, allowing for flexible, context-dependent behavior. Third, local variation and selection, the capacity for different brain regions to adapt and specialize while maintaining their connections to the broader network. These principles suggest a radically different approach to artificial intelligence. Instead of training monolithic networks on massive datasets, imagine AI systems that grow and develop like biological brains. Core processes would be encapsulated into stable, reusable modulars. Higher-level regulatory mechanisms would control how these modules interact and combine. New learning would occur through local adaptation that preserves existing knowledge while expanding capability. Early experiments in this direction show remarkable promise. AI systems built on developmental principles can learn continuously without catastrophic forgetting. They can explain their decision-making processes in ways that current black box models cannot. They can integrate symbolic reasoning with pattern recognition, combining the best of traditional AI with the power of modern machine learning. The implications extend far beyond technical improvements. Medical AI that accumulates knowledge over decades could become the ultimate diagnostic partner, never forgetting a rare condition while continuously learning from new cases. Autonomous systems that adapt and grow could navigate our complex world with unprecedented sophistication. Most importantly, AI built on biological principles could finally bridge the gap between artificial and human intelligence, creating transparent partners we can understand and trust. The Algonauts Project 2025 challenge represents more than a competition. It's a fundamental shift in how we think about intelligence itself. By forcing AI systems to match human brain responses to complex naturalistic stimuli, the challenge pushes beyond the current paradigm of narrow specialized systems towards something more ambitious, artificial intelligence that truly understands the world. The countdown has begun. As AI systems become more powerful and pervasive, the pressure to solve their fundamental limitations grows more urgent. The choice is clear: continue building ever larger black boxes that remain fundamentally brittle, or embrace the developmental principles that made biological intelligence possible. The secret lies not in abandoning artificial intelligence, but in recognizing that the most sophisticated intelligence system we know, the human brain, has already solved the problems that AI struggles with. The challenge isn't to build machines that think like humans, but to understand the principles that make human-like thinking possible. The revolution isn't coming. It's already here, encoded in the neural responses of people watching television, waiting for us to decode its secrets. The next chapter of intelligence, both artificial and natural, is about to be written, and for the first time in the history of AI, we have the human brain itself as our guide. The future of intelligence may not lie in choosing between biological and artificial minds, but in understanding how they can learn from each other. The Algonauts Project 2025 challenge offers a glimpse of that future, a world where the boundary between natural and artificial intelligence blurs, where machines and minds grow together, and where the ancient wisdom of evolution meets the cutting edge of technology. The question is no longer whether we can build AI that matches human intelligence. The question is whether we're ready to embrace the profound implications of success. Please like and subscribe, share this video or support the creator.